Iron has a specific heat of 460 joules per kilogram Kelvin. Aluminum has a specific heat of 910 joules per kilogram Kelvin. Wow, I want to pause for a second there because I think this actually has to do with where I'm going with this question. Is anyone surprised by that? Because iron seems like it should have a larger specific heat, you would think, than aluminum, at least if you cook at all. That might make sense, right? Using a large iron frying pan usually seems like it would be harder to heat that up or take more heat to do that than it would a flimsy little aluminum. And maybe I'm exaggerating the way I'm describing this, right? But it's kind of shocking to see that the specific heat of aluminum is nearly twice as much as iron, right? But there's more to the story because it says iron has a density of 7,850 kilograms per meter cubed, and aluminum has a density of 2,712 kilograms per meter cubed. So, the density might be part of the story. So, given two frying pans, one made of cast iron and one made of aluminum, that both have a volume of 100 centimeters cubed, what heat capacitance does each frying pan have? Aha. See, I was worried about the specific heat and thought it didn't really make sense that iron would have a smaller specific heat. But maybe when we do this calculation, we'll find out that if we look at equal volumes, the iron would have a larger heat capacitance. And that might make sense, right? That might make sense. And since iron also has a much larger density, equal volume would mean that iron pan would definitely feel a lot more weighty when I hold it in my hand, which kind of makes sense with my experience with frying pans in general as well. Now, we have formulas for this stuff, but in physics, sometimes the units can tell the story better than any formula ever could. So if I look at the numbers for iron, so maybe I'll write iron here because I'm going to look at that first. We're going to look at iron, and we have 460 joules per kilogram Kelvin. And the way that's stated is a little bit curious. It turns out that Kelvin really is in the denominator there, but I've seen units commonly reported this way, so I just want to make sure everyone had some knowledge that sometimes it's a little ambiguous. So like, is this joules per kilogram times Kelvin? But when you see this, it's actually the Kelvin is in the denominator. That makes sense for a specific heat because a specific heat is an energy per mass and per temperature, or the temperature part is also in the denominator, in other words. So I've got that. If I multiplied that by the density of iron, which is that number of 7,850 kilograms per meter cubed, let's look at what happens with the units there, right? Kilograms would cancel, and I'd have joules per Kelvin, but I'd still have a meter cubed downstairs as well. And I could say, like, well, what did that get me? That's definitely not a heat capacitance. What should a heat capacitance be, right? It should just be joules per Kelvin. And I have now, apparently, when the kilograms cancel, I have joules per Kelvin meter cubed. Well, if I multiplied by a volume, that would cancel that meter cubed, and I just have a joules per Kelvin. So without having written any single formula that is, simple or otherwise, I think I've arrived at a way of doing this. So maybe if I multiply by 100 centimeters cubed. One issue, though, is if I use centimeters cubed and meter cubed, I have to deal, I think, with the units conversion here. So maybe I should multiply by, let's see, I think it's, if I write this as meter cubed, I'm just going to put in a conversion factor here. It's actually, a meter cubed is equivalent to 10 to the 6 centimeters cubed. That's shockingly large. That's 3 kind of tiny there, but it's a centimeter cubed. The reason why is because each conversion of a centimeter would be a factor of 100, but 100 times 100 times 100, if you count all the zeros in that, that was 6 zeros, so hence the 10 to the 6. So this set of calculations I can put into my calculator and see what number comes out. And my calculator says 361.1, which maybe I can just round off to 361, and that should be in joules per Kelvin. And then if we do the aluminum numbers in the same way, that one's going to be 910 joules per kilogram Kelvin multiplied by 2,712 kilogram per meter cubed, and then we'll multiply again by the 100 centimeters cubed, and then by this conversion factor of a meter cubed per 10 to the 6 centimeters cubed. And you can check that a lot of units again cancel, so we're going to get something in joules per Kelvin, and this one winds up being 246.792. I'm going to round that off to 247 joules per Kelvin. And now things make sense, right? Because I started this story by saying, isn't it weird that the specific heat of iron is so small, when usually I would think of iron as being relatively resistant to changes in temperature upon the application of heat, whereas I would expect aluminum to the temperature to change relatively easily, that is. Sorry, I'm stumbling over my words there. And heat capacity really is the thing that tells that story better than specific heat does. But we can check in the slide and see that these answers are in fact correct.